Okay, this is a sticky situation. I have to. I have to introduce a chemical engineer that has a sense of humor. Foster Lyons has been a dear friend for a very, very, very long time, and he's a builder as well as a chemical engineer. He knows material science, building science, and he investigates building failures as well as prevents failures from happening by helping architects and engineers stay out of trouble. And whenever I have a complex question like adhesion, I call Foster. And Foster said, well, you keep asking these questions. I bet other people have those kinds of questions. I mean, I need an excuse to come to summer camp besides the good food and the alcohol. So Foster is going to talk about adhesion, and please give him a warm welcome.
Thank you, Joe. Thank you, Betsy. Okay, so I'm gonna talk about adhesion, and in the end, a little more specifically about what I would call practical, strong adhesion. Unfortunately, adhesion is a topic where the vocabulary is a little screwed up, like a lot of building science topics, but we'll find that. I think probably the room has lots of people that really know a lot about adhesion, and probably more than me, all kinds of manufacturers and people with PhDs and et cetera. But I think there were plenty of people that were like me a number of years ago where it was just a great mystery. And I'm somebody who arguably should have known about it. So I'm going to try to give you, my 90 minutes of adhesion, which is, some people might agree with it, some not. But hopefully it brings some understanding of adhesion and what I would call strong adhesion to you and arguably, the building science community. So, probably not anybody in the audience, but I certainly have experienced and participated in and probably started a lot of failures of various types on buildings, and pictures of some various failures that some of them I just scraped off of Google possibly, but some of them I've been involved with. There's flashing, peel and stick flashing materials that come unstuck, and roof membranes that get horrible blisters, and stones that fall off of walls, and peeling paint, and you get the idea. And stucco, and there's one picture there from the big dig where the ceiling collapsed, unfortunately. And what I've really have come to believe is, because I get asked by people all the time to come figure something out and tell me what went wrong and who's to blame and who can we point the finger at. But I've really come to believe that I shouldn't be assigning blame unless I really understand what's going on. I think Brian probably talked a little bit about that earlier. But if I can't explain this, meaning things that actually stick together, I shouldn't be trying to explain any failure. It's that, what was his name? John Stuart Mill's, like, it's not enough to know your side, you gotta know every side. And then I think it was Feynman who took it even further. He said, not only you have to know your side, you gotta know every side. So I'm hopefully gonna bring a little bit of that to you today. So I believe you really need to start at the absolute fundamentals of physics and the universe to really understand what's going on with adhesion. So these are the four fundamental interactions upon which, like everything else that happens to us and all thermodynamics and et cetera, in their essence comes down to these things. You can't really group any of these things amongst themselves. Gravity, electromagnetism, weak nuclear, and strong nuclear, okay? So I'm not going to say anything about nuclear forces today, so you can forget about those. I'm going to say, it's a big disappointment on the right over here. So I'm going to mention gravity once or twice in passing in the next couple of slides. And pretty much everything I'm going to talk about today is under the category of electromagnetism. And I'll explain why I believe that's important, and if you kind of keep that at the top of mind, I believe it helps to understand adhesion. So the first thing to know are the relative strengths, the range at which these forces, and the PhD physicists, don't get irritated with me for calling them forces, okay? Don't hate the game, not the player. And how they interact. Gravity, if we call gravity's force 1 on the scale, okay? Electromagnetism is 10 to the 36 times strong. What happened? Oh, now you got me. Electromagnetic is 10 to the 36 times stronger than gravity. Now that's such a big number, 10 to the 36, that it's hard for me to even really explain it. Like, there's approximately 10 to the 36 kilograms of matter in our solar system. It's that kind of number. That's like 1,000,000 times less than the number of grains of sand if you ground the earth into grains of sand. It's a really big number, okay? Relative, and we're all used to gravity, right? That's the way you got to think of electromagnetism. That's how powerful it is, okay? And its range is infinite, and it can either repel or attract. So try to keep that in mind and what an enormous number that is, okay? Just to really hammer this home, I guess there's no pictures at this particular conference, but if you had 2 pitchers of water side by side, and you got rid of all the protons, it was just electrons, the repulsion force would be about 10 to the 25th pounds of force, if we could weigh it that way, which, by the way, is the weight of Earth. So these are really super big forces. So luckily, they almost always cancel each other out on like a, human scale, so we don't notice them, okay? But at an atomic scale, they are totally, totally dominant, okay? So just try to keep that in mind. So let's think about this atomic scale. So down on this scale, where electromagnetic forces are totally, totally dominant. This is probably the image that everybody's seen, in 8th grade or something. Bunch of protons and a couple of neutrons in the nucleus, and the electrons spinning around. Now, it doesn't quite work that way, but it's fine to think about at the moment. And, you can't help but notice there's just gobs and gobs of space in there, even on the image that's drawn in your, 8th grade textbook, right? But it's much, much worse than your 8th grade textbook would make you believe. If this nucleus, and I think this is a beryllium molecule or atom here, if that nucleus was a baseball in the middle of like the Rose Bowl, the electrons would be at the outer, seats at the edge of the Rose Bowl. That's the kind of space we're talking about, And you can keep making comparisons like that. If the nucleus was, Red Sox, Fenway Park, then the Earth would be the electrons. It's an enormous gap of space in there, okay? So keep that in mind. But in that space, don't forget, electromagnetic forces, super strong. This is a quantum microscopic view of one hydrogen atom that had been a little bit excited, meaning they gave it a little bit of energy. So what you learn when you look at a photograph like this is it's not really empty space, okay? So what looks like empty space in your typical 8th grade textbook really isn't. And what you're seeing here is the probability of an electron being in a place. That's what the white, sort of whitish blue clouds are. If it's more blue, less probable, red or yellow, super probable, okay? So it's not really empty space. And because these forces are so colossally powerful, that's enough to prevent, 2 atoms or molecules from just passing through each other. That's the reason we all don't fall through the floor. There's a probability of electrons being there, and the force is so colossal, they never pass each other. They can't pass each other, okay? So keep that in mind. Now, this particular image, okay, that's showing some probability, right? And there's gobs and gobs of these sorts of images. If you do the mathematical model, what do they possibly look like? And in this one, you can see there's kind of like two, I don't know, crescents on the top and bottom. That's like less probable. And some people would like to tell you, well, if it's less probable, it's less of an electron, so that can attract a proton over here. I don't believe that, but it doesn't really matter. Don't worry about that for the moment, okay? But you're gonna hear that from other people. So this is just like a Google scraped image of what these clouds, these probability clouds can look like. And this is for hydrogen only. This isn't some crazy fancy molecule. This is hydrogen. You can see they're very complicated, right? So just kind of advance your mind a little. Well, what if it's a more complicated atom? What if it's a molecule? What if it's a polymer? What do these things look like? They're insanely complex, okay? And this is how things interact with each other, you know, in life on Earth and in our adhesives through these insanely complex clouds of probabilities of electrons, okay? So one of the results of this interaction of these insanely complicated clouds of electrons is something that has been noticed for hundreds of years. Newton even wrote about this. Turns out things attract each other. And I'm not talking about like, you know, boys and girls. I'm talking about like metal and rubbers and you name it. And this image here is a windshield wiper. And in England, this is about 30, oh geez, maybe more than that, 40, 50 years ago now, they were studying wipers to try to figure out how to make them work better, this or that or the other thing. And one of the things they realized was no matter how well they mathematically modeled the wiper on the glass, they realized there's always more rubber on the glass than they would ever expect. Greater area of contact, okay? And it turns out that phenomenon happens effectively with everything, unless it's magnetic or diamagnetic and you got an enormous magnet pushing it this or that. But kind of like all normal materials, this happens to. They attract each other. And this, in this particular case, it ended up being called the JKR theory, but this is things get pulled together. It seems really odd. Most people, I don't think, have ever heard of this before, but it's a thing. This is the truth, okay? And this, you know, then if you go get really smart people who know how to do incredibly sophisticated math, they're able to model this for simple atoms, in this case, hydrogen atoms. They have a low energy point at a certain distance between them, and that's what this graph represents. And that's the place where things like to turn out. Things are together, right? And if they get too close together, they start to repel each other. That's the uptick in the red curve there. But even as they separate out into infinity, they're still attracted to each other. And this is just something that is. It's the same way gravity is. This just is, okay? And this is just a graphical representation of it here. But the reality is everything. So I have my props. Hopefully everybody enjoys them. Every simple thing you can imagine, everything you can touch, everything you're sitting on, everything is just like these two balls. If they get close enough, they're actually stuck together to a certain degree. They're bonded together. And that's a super weird thing, but it's a real thing. And keep that in mind. So that's one of the bases of adhesion. So everything is sticky when it's atomically close, okay? Keep that in mind. So that stickiness, you know, now I'm going to start calling it a bond, because, you know, we always got to give fancy names to things. And then it gets fancier, you know, chemists and physicists have given all kinds of names to all these bonds. I'm going to tell you, who cares? It's just more important to know that it's bonded together. The details of the bond are not so important for the purposes of this description of adhesion, in my opinion. Just know they bond together, and there's an enormous range of strength of these bonds. Some of them are very weak. Imagine like the bond that's holding helium together in liquid helium. It really wants to become a gas. It's a crappy bond. But then like the stuff you blow up, like trinitrotoluene to make a bomb, those are very strong bonds. And then there's everything in between, okay? The names don't matter. There's just this range, okay? Just keep that in mind. Turns out, most of the bonding that's important for practical, strong adhesion are crappy, weak bonds. They're nothing like the strong bonds that hold oxygen and hydrogen together in water, like the actual hydrogen and oxygen, not the hydrogen. But, you know, anyway, these just kind of keep this in the back of your head. They're crappy, low energy bonds are really what we end up relying on in strong adhesion, which is really weird, but it's just the way it is, okay? So this is, for me, adhesion concept 1. And in the end, there's 7 of these. You're going to see them repeated on, like a row as I go on here. Concept 1, everything is sticky if the separation distance is just right between them, okay? Sometimes it's a strong bond, sometimes it's a weak bond, sometimes there's a lot of bonds, sometimes only a few bonds, sometimes they're flexible, sometimes they're springy, et cetera, et cetera, et cetera. But that's concept 1. Everything is sticky, okay? So let's move, and now because everything is sticky and because all of these, the way they stick together through all these crazy orbitals that I mentioned before, they can come together in a lot of different ways, in a lot of different configurations, et cetera. So here's some examples of things that are together, that we're going to call them adhered together, are just things close together, okay? Nothing else involved, basically. So this is a gecko, a picture of a gecko climbing up the glass in its enclosure. So that's just things on the gecko's foot close to the glass. There's nothing else going on there, okay? And by the way, they have about 4 times more strength than they need. They can't do this on Teflon. Unless the Teflon's wet, then they can do it just fine, which is super odd, and might get to that later. This is another example of things just bonded together, adhered together because they're close together. So the typical metal for a mirror these days is aluminum, and it's just close to the glass. That's it. That's the only thing holding it together, okay? Dr. Dupuy, this is an image from his presentation last year where he tested a lot of roofing materials. So the question becomes like, okay, how strong is this just close together bond, okay? So to give you some reminder of strengths of things, so last year, Dr. Dupuy told us about all sorts of things, some of them, failing earlier than others, but if I'm getting this right, they stopped when the gauge indicated 2,000 pounds of force per square foot. Hopefully I'm getting that right. So in other words, like, that's really strong, 2,000 pounds a square foot, okay? And I don't want to, it's a little confusing, but the adhesion involved in that's getting tested here is more than just close together, but the purpose of what I'm talking about right now is just to try to get your mind around the strength of the strength of strength, okay? So, anybody ever seen these gauge blocks? A couple people, 5, 10, 20 people maybe? I've got some here. I'm going to pass them around. People can play with them. This is 2 pieces of metal. These are gauge blocks. They're used by people who do machining for precision tools to measure distances and to check how they're doing with their machining. They're not magnets, and these are made out of steel, but they can be made out of ceramic, just a non-metallic material. And there's no glue between these 2 pieces. These are just 2 pieces of metal together. Ray?
Not magnets.
Not magnets, but you guys can play with them. Do whatever you want with them. If somebody finds them to be magnetic, chuck it at my head.
So, are they called Joe blocks as
They are called Joe blocks because they were invented by a guy named, I think it was, in English would be Andrew Johansson. So they're named Joe blocks, correct. So there is actually a tiny little space between those two blocks, and it's about 25 nanometers, I believe, which is about the equivalent of 100 water molecules in a row. And that's it, okay? The amount of force you'd need to pull those two things together, if you get them well put together, is about 70,000 pounds per square foot, okay? So wrap your head around that. The guy that we really trust to tell us whether something's really well adhered to a roof stopped testing at 2,000. And this little piece of metal, you can put it together in front of you today, holds itself together with a force of about 70,000 pounds per square foot. That's how powerful that force can be. Now, why don't we do that for adhesion? Why don't we stick these little metal things on our roof? Because it stinks for practical adhesion. We'll get around to that. It's crazy strong in one direction. It's crazy lousy in every other direction, all right? But just to give you some idea of how much force we're talking about with these crappy little bonds over 100 nanometer gap, that who knows what's in there. Maybe there's a couple of water molecules holding hands. Maybe there's a couple of oxygen molecules holding hands. Maybe they're not holding hands. Who the hell knows? It's just crap close together that wants to be close together. The secret of these blocks, by the way, is the fact that they are what is called optically smooth, okay? So they're not rough at all. So you can get a lot of steel molecules very close to a lot of other steel molecules. Ray, there's a lot of people in the room. If you're going to play with it the whole time, nobody's going to get a chance. Okay, here's another similar one. Anybody here ever worked in a laboratory with a lot of glass, you know, and stoppers and this and that? You ever get a... It's a pain in the ass, right? Turns out, you can, you know, we use cork these days in our wine bottles. You don't need to. You could use glass stoppers. So this is an image. This is actually my photo. I didn't steal this off of Google. So that stopper you're looking at there, as God is my witness, Hercules couldn't pull that thing out if he tried, just pulling it straight out. But you can twist it, and it comes right out. Piece of cake. Very interesting. So this, you know, you can see the full wine bottle. You can still buy these things today. It's not so many, but they're out there. And you can take it, shake it upside down, pull it. The wine doesn't come out. The wine doesn't drip out. Nothing. It's just glass against glass. There's nothing in there but glass against things close together. That's what's holding it together. But again, twist it, it's out. Useless. So that's, you know, surface bonds, okay? So I got to talk about surfaces. It's got,
Broken, they don't stand.
they're broken? What did you guys do?
We broke it. What we did is bounced it off the floor, so I think it got dusty.
Could be. Could be. Who wants to try to put it together?
I'll be the engineer. I'll work on it. Just skip that from her.
What's the problem? We're gonna try some new people, okay? Yeah, maybe your dust helped it. I don't know. Could be. Anyway, surfaces. So this is, again, one of these tunneling electron microscope images. This one's opal, kind of a fancy bit of quartz. But there's this famous expression by a fellow who's no longer alive, Wolfgang Pauli. God made the bulk. Surfaces were invented by the devil. And all the adhesion I just talked about happens at the surface, so I got to talk about surfaces a little bit. Consider how a surface is made. So this is just a 2D image of what should be a 3D thing. Imagine a lattice of atoms all bonded together really beautifully like this. So if along that dotted red line, if I was able to clip all the bonds or measure the strength of all that bonds, the typical material that we would typically build things out of is about 1 joule per square meter. That's the amount of energy in all those bonds, okay? About a joule per square meter, you know, more or less. So that's 1,000 millijoules, okay? So if I break it, I separate those two, you get 50-50. So now the new surface you have is about 1/2 joule per square meter. That's the surface energy, you know, if it's a liquid, we'd call it surface tension, but solids, it's surface energy. So typical thing, you rip it apart, that's about 1/2 joule per square meter. The problem is, the moment you rip things apart, oh, I'm sorry, I'm gonna go for this. And so here's some example surface energies for all sorts of materials. So, you know, 2/3 of this screen, the right-hand side, is a lot of plastics and polymers and et cetera that, you know, you might be familiar with, PVC and polystyrene and et cetera, et cetera. And the biggest number there is 50, so that's 50 millijoules per square meter. And the last screen, don't forget, was 500. Silicone's 24, what do you call it? Teflon, 18. So Teflon, everybody knows, like, you know, we all, it's a crappy surface, almost no surface energy, right? We'll get to that. And on the left side here, it's a lot of metals and water, and it's even down to olive oil. They're pretty big numbers, 1,000, 500, et cetera, et cetera. Okay, so that's about the range of surface energies we're talking about when we create a new surface out of a, you know, a solid material, all right? The problem is, if you do create a new surface out of anything, very quickly it gets dirty. It reacts with anything that's in the air, depending on how it wants to react, how all those orbitals go together. So it can react with water. Water can get, don't forget, things like to stick to each other, right? Everything's sticky. So oxygen and nitrogen and et cetera, et cetera. That happens like 1 or 2 seconds. Unfortunately, then your surface energy goes down to like 100 millijoules, okay? So it loses like 1/5 of what it was just 1 or 2 seconds ago, all right? And that's just to bring it all home for everybody. When you try to light a fire by making sparks with, you know, flint and steel, that's what you're seeing there. That's the steel, newly created steel surface burning. That's it. That's how fast it happens. The moment you strike the flint and you create a new little tiny chunk of steel that has no dirt on its outside surface, it reacts instantly and it burns. So that's what you're looking at there. You give it another couple of minutes and the surface really becomes a mess. It starts interacting with pollen and VOCs and maybe some more water, you name it. And this is just you know, trying to give you a visual image of what it might look like. And this is sort of the typical surface energy of plastics typically, but almost anything after a couple of minutes sitting out on your counter. So almost everything has kind of the same surface energy when it's just laying around. Anybody making any progress with those gauge blocks? Got it? I think if anybody who gets it, they should like stand up and just like wave around, you know, like for sure. Anyway, so keep those numbers in mind. You started when the thing was put together. It's about 1,000 millijoules. You split it apart, 500. You know, it reacts immediately. You're down to 100. Give it a little time. You're down to 50 millijoules, which is, you know, about the same as most plastics that we're used to seeing. So you go to buy some flashing tape and you read the data sheet that comes along with it, and they'll tell you that their material has an adhesive strength of about 500,000 millijoules per square meter, okay? So how the hell could that be, right? That's 10,000 times more than the surfaces we were just talking about. In other words, if all the bonds on the surfaces just one slide ago could only make 50 millijoules, how the hell do you make 500,000? And that's the trick of adhesion that I'm hoping to explain to you over the next couple of minutes. Okay? Now, mind you, I've already thrown kind of a mean trick in here to convert newtons per meter into millijoules per square meter, but probably only a couple people in the audience caught that and they didn't call me out on it, so let's just leave that alone, okay? So I'm going to summarize kind of these strengths and put some vocabulary on it. These are the typical strengths of adhesion, okay? So the surface bond adhesion that I've spent the last 10 or so minutes talking about, that's the top of the screen there. That's typically less than about 500 millijoules per square meter, and we'd call that, that's weak in terms of like real world adhesion, stuff that's useful, okay? The middle is, which is about 10 or 100 times stronger, intrinsic adhesion. And that's like, you know, you pick a cobblestone up off the ground, like what the hell's holding the left side to the right side? That's intrinsic adhesion. It's about 500 to 50,000 millijoules. That's modestly strong, which sounds crazy, like it's hard to pull a stone apart. But in terms of practical adhesion, it's actually quite useless. We'll get into that in a minute. And then there's practical strong adhesion, like the tape I just showed you on the last screen. That's over 1,000 millijoules per square meter. That's strong. That's the kind of strength we need for practical strong adhesion. And by the way, 50,000 is about 3 times stronger than what you find on a Post-it notepad. Like that's how weak and crappy the adhesion with a Post-it notepad is, all right? So, and again, it's these weak bonds that I've got circled there, hydrogen, dipoles, you know, van der Waals, blah, blah, blah. But the names don't matter. Just know that they're all very weak bonds. That's the stuff that's on the surface there holding things together. But strong adhesion is not about the strength of the surface bonds, okay? But you gotta have a couple. If you don't have any surface bonds, things don't stay together. But if you have a few, it works, and you can make it work. And that's the key to strong practical adhesion, all right? So you need a few, but they're really not that important, and it's not important how strong they are. And there's a lot of talk and a lot of confusion about the importance of surface energy for our various things. It's really not so important. To give you some idea, this is a non-stick frying pan. That's a tiny little piece of tape doing great. No trouble. Ray, want to try it? This one? You going to be okay with it? You can pass it around. It's okay. You can probably even pull it off and put it back on. Oops, sorry. So even Teflon, who we all kind of agree is the crappiest surface energy material around, we can bond and adhere things to it very easily and well. If you know, it takes the right materials and a bunch of stuff, but it's not as difficult as people think. All right, so that's adhesion concept 2. Atom to atom surface bond adhesion is necessary but insufficient for strong practical adhesion. Meaning, you know, with those two gauge blocks, it's crazy strong in one direction, crazy useless. But it's still these very weak bonds that all make it happen in the end. So surface energy is almost insignificant regarding strong adhesion, okay? Polymers. I got to start talking about polymers because almost every adhesive that is practical in the building industry is made from polymers. And as humans, we've been using it forever. And 50,000 years ago it was birch bark, and 1,400 years ago it was beeswax, and today it's epoxies. But 100% of our strong adhesives are polymers or polymer-based. These are very long chain molecules. Most are organic. Some are inorganic, like silicone or aluminosilicates, like, Portland cement and that sort of thing. So this is a graphical image of 2 polymers just put together, close. You just put 2 polymers, stick them together, okay? So now we all know everything is sticky to some degree, right? You always get some surface energy adhesion there, some of these surface energy bonds, and they add up to about 100 millijoules per square meter, okay? That's not horrible. If you try to pull them apart, it's not the end of the world, but that's the kind of energy and strength we're talking about when 2 polymers are just close together and there's nothing else going on other than them being close together, okay? But polymers are fuzzy, as it turns out. The surfaces are fuzzy anyway, and this, I don't have any images of polymers that close up, so I used a tennis ball. This is the way you should think of polymers. They're a little fuzzy around the edges, okay? Some are more fuzzy, some are less fuzzy, some have short fuzz, some of the fuzz is wriggly and it's always moving, but always a little fuzzy, okay? And polymers can dissolve into each other, usually. Sometimes they don't like to, but they can. So, and you can think of that, this is called intermingling. You can think of that like sticking two hairbrushes together or two toothbrushes together or that sort of thing. That's the image of intermingling. And you put two blocks of polymer together, that's kind of what they do. This is an example. These are made out of urethane, as far as I know. I'm not 100% sure, but I'm pretty sure. These are urethane, okay? And there's nothing. These are dirty, they're scratched, they can dragged along a garage floor, so they're not optically smooth like the metal there, right? I just take these things and just do that. Whoop. Didn't work so good. Foiled, but normally, there we go. They just stay together. And that's because there's a little bit of that contact, surface energy adhesion I mentioned before, and a tiny little bit of intermingling, right? Maybe I start over here, huh? Anybody want to play with them?
That got a ceramic finish on there?
No, I don't think. But I'll let you play with it and you can figure that out. But I really don't think so because ceramics, it doesn't have the same fuzz. You wouldn't get that intermingling. And we'll get back to ceramics and non-stick pans too. You can also think of intermingling for all the carpenters in the room or anybody who's built a wood frame house. You know, when you stick nails through one board and it goes into the other board, that's the equivalent of intermingling. And in fact, the mathematical modeling for the two processes is effectively exactly the same. It's the same basic formulas. Okay, so keep that intermingling in your mind. And this is a kind of a fantastic hand-drawn image of intermingling between two polymers because polymer chains are enormously long. So this is now two polymers together with surface bond adhesion and intermingling, okay? Keep that image in your head. So the strength of that sort of adhesion is about 10 times more than just surface bond or surface energy adhesion, okay? So now we're up in the range of about 1,000 millijoules per square meter to give you some idea. So we've jumped from about 100 to about 1,000, okay? With just this intermingling thing, which happens with polymers, and we're always using polymers for the vast majority of our construction grade adhesion, all right? So that's adhesion concept 3. Intermingling of long molecules across the interface, the thing between the two of them, increases the strength of weak surface bond adhesion up to something moderately strong, about a 10-fold increase, okay? So there we go. Now, but polymers are super long, like tens of thousands of monomers put together. So they get tangled up, just like the wires in your drawer, okay? And you try to pull one out and they all come out, they're all tangled up. So that's a thing. Now you have entanglement, okay? So when you put two polymers together, they intermingle because they're fuzzy and they can dissolve in each other a little bit. But that intermingling, it can get longer as time goes on and they start to entangle with each other, all right? And there's just a little highlighted image. The definition of entanglement is the chain has to cross the interface 3 times, but who cares, right? And nobody ever counted the wires in your drawer. You know entanglement when you pull the wire. So this kind of strength, this is where you start getting, and the reason we start getting very strong practical adhesion with the kinds of polymers we use every day in the building industry. This is about 100 times, or increases the strength by 100-fold from what we had with just entanglement. And it's whatever, it's a million-fold, plus or minus, more than just the surface energy bonding, all right? Concept 4, entanglement of long polymer molecules increases the strength of surface bonding adhesion plus intermingling to something truly strong and useful. 100-fold increase over intermingling, okay? So that's like the trifecta of really what's going on behind adhesion: the surface energy bonding, intermingling, and entanglement, okay? So, and by the way, if it's not two polymers, if it's like glass and a polymer, so the glass isn't fuzzy, it's not reaching out into the polymer, you have the surface bonds, and then you have internal entanglement. All right, and I'll talk more about that. And for anybody who knows about PSAs, this is a super big deal thing. But it's the same thing going on. It's just, you know, all on one side. All right, without the, and there'll be more on that. Whoops. So the question becomes like, all right, how many bonds? These surface energy bonds. And you're like, wow, wouldn't it be, boy, more would be better. And if we have more, why don't we make them super strong, right? Let's figure out the chemistry and make it really super strong. Turns out that's a mistake. You're better off having a lot of crappy, weak surface energy bonds than having high energy, hard to break surface energy bonds, like what we would call chemical bonds. If you have more than about 1% of strong bonds on this interface surface, your adhesion sucks. It's just not going to be practical. It's just it turns out it's too stiff. You need crappy bonds. So about 1% is what you're after, or works best. So primers, okay? Primers are a thing. A lot of manufacturers require them for various materials. Well, what's going on? Well, it depends on the material that you're bonding to. So it turns out some primers are better than the primary adhesive for developing surface energy bonds to the whatever surface you're trying to bond to. And there's a little tail of polymer off those individual surface energy bonds from whatever primer you're using. And it turns out that tail mixes very well with the adhesive you're going to put on top of it. So it's just, the primer is just giving you, the biggest thing it's doing for you, probably not the only thing, is just allowing you to make a good surface energy bond, and then it's intermingling and entangling very well with the adhesive you're actually going to use, okay? But it's still, I haven't explained why the hell all this entanglement and intermingling is 100,000 times, or 1,000 times stronger than just the surface energy bonds I mentioned. So I need to explain all that. So to do that, it helps to understand how uniform materials behave and how they break. And that's like an entire 1 or 2 semester course for most civil and structural engineers, so I can't go through that whole thing. But the mechanism and the understanding is approximately the same, okay? So if you look at a three-dimensional material, this is a two-dimensional image of it, and you tried to pull it apart, these purple arrows are just the indication of the stress lines. You're trying to separate left from right. And the stress goes through all the atoms and through all the bonds between them. And if your material doesn't have any defects in it, it's any place you cut it, all the stress is uniformly distributed, okay? But if you have a defect and an edge somewhere, these stress lines start to concentrate at the point of the end of your defect, okay? So here I've shown it as there's 3 or 4 stress lines that are all concentrated within the space of like the distance between 2 atoms. In the vast majority of cases or materials, that sort of increase in stress is far more than the individual bonds between those atoms can withstand. So once you have a crack in materials, if there's any kind of force applied, the crack almost always advances, all right? The crack propagates. And that's a big topic for adhesion. That'll come up again, but this is how failures happen, okay? A little bit of force, and the local force becomes greater and greater and greater. It overcomes the local bonds within the material, and the materials break, okay? So that's adhesion concept 5. Adhesion failure is always crack propagation. And I know people are going to say, well, what about cohesive failure and this, that, and the other thing? We'll get back to that. Doesn't matter where it fails or how it looks. It's always crack propagation. One material separated from another, okay? So there's this thing, what engineers have put a word on it, dissipation. If those stress forces I talked about can be spread out within the material, so you reduce a local stress concentration, if you dissipate that stress, you now can get below the break threshold of the individual bonds that it's acting on, okay? So the energy is applied across more bonds. And eventually, that energy dissipates itself either as heat or as sound or as, it can also be radiation, sometimes X-rays and weird stuff like that. But if a material has an ability to dissipate stresses, the crack stops. We don't get crack propagation, okay? So that's a super big deal. So with entanglement in polymers, it turns out polymers are fantastic at dissipating these concentrated stresses. Stresses just do not concentrate in the material. They get spread out along the length of the polymer, and one polymer sliding against another reduces some of the energy, et cetera, et cetera. So polymers or entangled polymers are fantastic at dissipating these stress forces. And this is just a little pictorial, but to give you some idea, you know, there, on the far right there, that's a polyethylene chain. And if you pull the two ends, you know, it stretches. But that stretch is applied across all the elements of the chain, so you have to pull it a lot. And I got one other, you know, prop here. So if you imagine a single bond, and imagine it like a rubber band, like this, you know. If I pull this far enough, right, eventually it's going to snap, right? Hold that up to your face. I'm just kidding, come on. Right? Eventually, right, it breaks. And you know, the amount of energy I had to put in is the force I had to exert, and the distance over which, so I might have to pull this 20 feet, but eventually it's going to break, okay? Force is, you know, force times distance. Now I really do need somebody to hold it.
Go.
Yeah. So now imagine a polymer, right? This represents a polymer. There's only 4 of them here, but, you know, any one of them, force times distance, it breaks. 4 of them, it's the same force. I got to go 4 times further. It's 4 times the energy, okay? And that's what's going on. Thank you. That's what's going on in entangled polymers, except a shitload more than just 4, right? They're great at dissipating this energy, right? Okay. And this is a pictorial image, but it's not just individual chains. They're all wrapped up amongst each other. Sometimes they're cross-linked. They're all over the friggin' place. So it has this incredible ability to dissipate the forces that are applied to it just by the nature of the material itself, okay? And does that make it 10 times harder, or you got to put 10 times more energy in, 1,000 or 10,000? It depends on the polymer. Depends on all sorts of things. But that's a big deal. So back to those gauge blocks, they're incredibly strong. It means 70,000 pounds per square foot of what's called butt pull strength, okay? Incredible, right? But there's zero intermingling, there's zero dissipation of forces, there's zero entanglement. It's super easy to propagate a crack. For anybody, where is it now? Where did it go? Oh, way down there, holy smokes. Oh, you got it together, good for you. Did you guys, is somebody using glue, super glue down there? No. So anyway, it's apparently, you guys have all realized, like, it's super easy to undo. You just crack it, like a I don't know, pretzel or something. Very easy, even though the other way is quite difficult. So it's useless, whereas this intermingling and entanglement is extremely useful. It's hard to break. It doesn't want to come apart, basically. So, all right. And this kind of brings us to no stick. I think if I gave this presentation the second time, I'd move this slide, but anyway, you know, that's what's going on with non-stick pans. There's no intermingling and there's no entanglement. Somewhere, where's the pan now? Who's got the pan? There, is the tape still on it? Oh, it's still on it. Somebody moved it. Awesome. Is it still kind of sticky? A little bit. Okay, we got more tape here if you want to put some new tape on. But it's not impossible to stick to a non-stick pan. But without intermingling and without entanglement, things don't really stay stuck. And the pan itself, the surface isn't optically smooth like the gauge blocks. They're always a little bit rough, right? They're a little something about the surface. So that little bit of roughness and the fact that you got very weak surface bonds only, it's very easy to start and propagate a crack. So stuff just doesn't stick to it. So keep that in mind. That's now, cast iron pans that are very not sticky, the science is a little different, but we could talk about that over wine tonight. So, back to the slide that I thought I really needed to be able to explain this before I point the finger at somebody for screwing up some adhesion problem on a job site. Bubblegum is a very weak polymer. If it was a strong polymer, you wouldn't be able to chew it, right? There are very weak surface bonds when it gets to the bottom of your shoe or the concrete sidewalk. But it has great internal entanglement. So, and that's kind of what you're looking at there. As it starts to pull apart, you can sort of see these long polymer chains all kind of like, the same like pulling out wires from your desk drawer. You're like, ah, crap. And they just keep coming, right? So imagine if you stapled a couple to the bottom of the drawer, you'd never pull them out. So, and this is modestly strong adhesion, and that is the way our practical adhesives work in our industry, all right? And this is just another picture, same thing. This is it's a weak polymer. You can tell it's weak because when you pull it and it really stretches like that, that's just an indication that it's weak. But there's enough of these very weak surface bonds. There's not some crazy chemical bond between the polymer and this painted metal. It's not like, some fancy chemist came in and made some super strong bond. No, it's a crappy, weak bond between the polymer and the paint. The dissipation of the forces that are being applied by this person trying to pull the tape off are dissipated in the material. And that's what's giving it the strength, okay? Great dissipation, strong adhesion. All right, and this is kind of, I don't know whose material this is, but one of them's green on a surface and the other one's black in the tape. So it's, same thing. It's a weak polymer, but it's got enough of these surface energy bonds to hold the polymer to the material. There's great dissipation. There's probably a little bit of intermingling, although I'm not sure of that at all. But there's certainly great internal entanglement within the adhesive that's on the tape. And as a result, you get tremendous reduction in crack propagation, and you get strong adhesion. All right? This is an epoxy adhesive on a bolt in some concrete. So epoxy adhesives, structural epoxy adhesives, are actually very tough polymers. They're tough, for lack of a better word, right? They're not like crappy, weak bubblegum polymers, right? And again, weak surface energy bonds. That's like the bond between the epoxy and the metal is a weak surface adhesion bond, and the bond between the epoxy and the concrete is a weak surface energy bond. There's not some super strong chemical bond in there. It's crappy, weak bonds. But the epoxy polymer between them does the work for you. With these kind of bolts, there's a tiny little bit of mechanical interlocking also, and because the polymer is so tough, it can kind of get stuck there. But it's really the polymers doing the work for you by dissipating the forces, so it doesn't, even if a crack starts, what would normally, like your windshield breaking, it just continues at the speed of sound, it gets dissipated into the material, and that absorbs all the energy, all right? So that's adhesion concept 6, dissipation of forces promoted by entanglement and intermingling, mitigates crack propagation. And number 5 right below it says adhesion failure is always crack propagation. If you can mitigate crack propagation, you can prevent adhesion failure, and it stays strong for you, all right? So this is normally what everybody that I talk to about adhesion wants to talk about. They just want to know, like, that's great, Foster, but just tell me which tape to buy, right? Like, yeah. So there's like a bajillion and one choices for any kind of adhesive application you want, like tapes and glue and spray on, you name it. And this is just a picture from a local hardware store to like just remind you of how many choices there are. 1,000,001, right? And they're all different, and they're all for different applications, et cetera. And this is the thing, okay? There's an infinite number of chemical combinations of the adhesive itself, meaning the polymers and the things you add to the polymers, et cetera. So you can make like 1,000,000 different adhesives just by changing the chemistry, okay? And that changes all kinds of things. It changes how it bonds on the surface, it changes how it intermingles, it changes how it entangles, and unfortunately there's 1,000,000 combinations there. There's 1,000,000 different mix ratios. We normally don't make adhesives out of a single polymer. We mix a bunch of things together to change its viscosity or do this or do that. There's 1,000,000 combinations. And I'm using million like, it's probably more like 10 billion. But anyway, just to give you an idea. There's an infinite variety of physical properties. Some, like silly putty, can kind of retain their shape for a while, but then they get lost in your, shag carpet. And there's others that are very stiff, and then epoxies are crazy stiff, and et cetera, right? And those can all be engineered. Like the formulators know how to formulate different physical properties in the various polymer mixes. And there's an infinite variety of adherents, the things you want to stick to: glass, wood, carpet. Hell, just look around the room. This is stuck to the wall, and the carpet's stuck to the floor, and these screens are probably 7 layers all stuck together, and the label's stuck to my plastic. On and on and on. 1,000,000, right? So everybody always wants to talk about, like, well, let's talk about this exact adhesive from this exact company because that's the best. I'm of the opinion, like, I was hoping to explain, like, what's behind all of that, or above it, so to speak. But just keep in mind that this, like what's on this screen right now, is normally what we're all talking about when we're talking about adhesives, because we sort of bypass the, like, how the hell does it really work physically? Kind of want to know, like, well, is this going to work for me today on this job, And I get it. But that, unfortunately, requires an adhesive sommelier, and that's not me. So, also, Peter, where's Peter? Peter, how are you? I actually forgot to mention something earlier that involved you. Don't worry. Now that I've remembered it, I won't forget to say it.
I'm here for you.
Yes, thank you. So, time is a factor, meaning if there's a stress on two things adhered together, the time over which that stress is applied is a factor. Anybody ever here pulled a Band-Aid off very slowly? Hurts, right? Compared to like ripping it off fast? Well, that's exactly what's going on there. The speed is a factor in how well things adhere together, as crazy as that sounds. And same as temperature. Fast is brittle, slow is relaxed and not brittle, and cold is brittle and hot is relaxed. So, Peter, the thing I forgot to mention earlier, where did he go? Oh, there you are. Was back when electromagnetic forces are so strong. I think you're the only guy that I remember who wrote first law of building science is that physics trumps chemistry. I don't know, 10 to 36 is a pretty goddamn big number. So, anyway. This is a graph of no particular importance other than to show you the variety of properties that polymers have. So on the vertical axis is oxygen permeability, and on the horizontal axis is water vapor transmission rate, okay? So, and then all the little diamonds are, where various polymers, typical kind of everyday polymers, are they Cellulose is incredibly high on water vapor transmission, but kind of low on oxygen. And I don't know, polystyrene, that PS on the top right there, that's, you know, much lower on water vapor transmission, but much higher on oxygen. And the one on the very bottom left there, I think that's Kevlar. Seems like we should be using that underneath all of our concrete slabs, it looks like. So, you know, they all have these different properties, and that's, you know, they can all be formulated for that, but just keep it in mind. There's 1,000,001 choices with 1,000,001 variables, all right? Anybody here remember BSI 047? And I'm not talking about you AI guys who can look it up real fast, but this is an article Joe wrote on bricks, and how they behave in freeze-thaw, and it was, I don't want to call it a summary, but the fellow who did it was Peter, I believe is how you pronounce his name. He might be in the room. Is he in the room? Not in the room, sorry. Anyway, long story short, it turns out there's a critical saturation level for bricks of about, you know, 0.7, 70% saturated. If it freeze-thaws and it's more than 70% saturated, they tend to start breaking apart. Less than 70, they stay together. There's a similar thing for polymers and adhesives, okay? So this is on the vertical axis is failure load in kilonewtons, and on the horizontal axis is relative humidity. So this particular adhesive maintains its strength up until about 60% relative humidity. Above that, it starts to drop off. Very similar to that S critical for bricks falling apart. And it's kind of related, I think, although it's not worthy of spending more time than this to just tell you, yeah, relative humidity can have an impact on adhesion strength. And remember in the last screen, water goes through all of the polymers eventually, okay? Just keep that in mind. So, this is adhesion concept 7. The quality of force dissipation is a function of the chemical and mechanical characteristics of the system's materials, which is the adhesive, the adherent, and whatever else is in there, and temperature and speed of force application, okay? And unfortunately, this is where, like, everybody in the industry spends the most time. The quality of force dissipation is a function of chemical and mechanical characteristics, and everybody's always talking about viscosity and tack, and, you know, they get better silane bonds and blah, blah, blah. Okay, it's all true, probably. But those aren't the fundamental concepts that I think we should all understand first, okay? So, let's look at some failures. This is just a representation of two adherents, the blue things, with some adhesive between them. This is ideally what it would look like when things are well together, and et cetera, right? And, you know, the standard dogma is, well, it fails in 2 ways. It's an adhesive failure or it's a cohesive failure, right? It can fail in those 2 ways. But there are many, that's I believe, an inadequate way to try to figure out how things failed, or an inadequate description of the failure mechanisms that are possible, okay? And this is just a little pictorial to try to help out. The one on the top left there, that would be adhesive failure. In other words, the adhesive just left the adherent and didn't leave anything behind, didn't anything. But the one in the middle and the top there, that's an indication that, well, you know, those little nails might represent your primer, but, you know, they stayed in the adhesive, they didn't stay on the adherent. But the opposite couldn't happen, or could have happened. I didn't draw it that way, but you can immediately imagine, like, well, what if the primer stayed stuck, but the entanglement and the intermingling is where it failed? That's a very different failure. And I don't think it does it justice to call it cohesive failure. Calling it cohesive failure didn't really do a lot for you. Where's Brian Hubbs? See, right? Like, you gotta know the whole story, right? Come on. You people think it's hard coming after Brian and John and Hartwig. Come on. Anyway, and then top right, that's true, cohesive failure. Maybe they're just a adhesive polymer somehow came apart. Bottom left, cohesive failure. Bottom middle, you can get, you can get a little bit of mixing of all the things, and then it somehow breaks apart, and it's not at all clear whether it's cohesive or adhesive or something else. And then sometimes, like this cohesive thing, it just like stretches and stretches and stretches so much, it's hard to start, they might have kind of separated it enough that we might call it failure, but it's not really failure totally. It's not, so it is, anyway. And you can have structural failures and there's more. It's more complex than just cohesive and adhesive failure. Keep that in mind. And hopefully all that talk about 10,000 monomer chains of polymers give you that idea. How am I doing on time?
5 minutes.
10 minutes, that's all? So, some failure images and talk here. So this is just, something you'd see every day if somebody's putting down an underlayment on a roof. It comes with this silicone release tape on it. They pull it off and they stick the sheet down on the roof. Well, that's adhesion failure, pulling that silicone release material off. And that's just crack propagation. That's all that's going on there. And the reason we use silicone materials rather than Teflon, because you'd think, wow, Teflon, right? The crappiest surface energy in the world. Why don't we use that? No, the reason is the same like whatever the pan is with the tape. What's going on at the surface, there's a particular property of these silicone materials that doesn't exist in the Teflon materials. They actually behave like liquids at their surface. So as you apply force, the point at which the force is applied behaves like a liquid, not like a solid polymer. So they just peel right off. Teflon wouldn't do that. It's completely useless as a separation material. I already talked about the pans, so there's no intermingling, no entanglement, so there's no fuzz, and that's the reason they work. All right? Mirrors, you've probably all seen this at some point on mirrors, at the bottom, if you get water drops down there, all of a sudden the glass separates from the aluminum, and that's just water diffusion along the interface. So you're losing those surface energy bonds. Literally, the water molecules are just bumping the limited number of crappy surface energy bonds that existed there, right? And this is very common, by the way, in construction failures. Water causes a lot of trouble for construction, and that's it. And it's because of this, I think, this thing that we call permittivity, not permeability, not permeance or any of that. A new P word for all you building scientists, permittivity, which is a relative measure of chemical polarity. Water is incredibly easy to polarize relative to almost everything else in day-to-day life, and this is the list of it here. Glass is only 6.85, ethanol 24, water's 80. There are other molecules that are easier to polarize, but they're a little bit unusual. So the fact that it's so polarizable and the fact that electromagnetic forces are so GD powerful is the reason that water ends up in places versus other molecules like polymers, okay? And keep in mind that, so now's the one time I'm actually going to talk about the names of these things. The hydrogen bonds are in the middle of the screen there and kind of middle energy around 10 kilojoules per mole. That's actually stronger than a lot of the crappy bonds that hold adhesives at the surface together. It's stronger than dipoles, stronger than these London dispersion forces. So if water's around and it makes a bond, that stronger bond ends up in a lower energy state than the crappy dipolar London dispersion forces. So it bumps them out of place and they don't get replaced. They stay in. Skip that one. This is some pictorial examples of some polymers that just didn't have much intermingling. So you've probably all, if you've been out on a job site, you see this. Sometimes things are sort of stuck together, but not so good. And it's pretty obvious that they're not so well stuck together, but it's not horrible. And that's all that's going on. There's not a lot of intermingling, and there's very little entanglement. So it's just not so strong, but there's a little bit, so it's not so horrible. Is that failure? I don't know. Sometimes it is, sometimes it isn't. This one is total failure. So that's the self-adhered material and the green stuff there on top, and that's concrete below it. And you can see that some of the adhesive material is still stuck to the concrete, right? So, and it's come apart cohesively, more or less. And, so you still, these surface energy bonds still exist. So the material broke not right at the surface. It broke within the adhesive. So something went wrong with either the intermingling or the entanglement. That could be a lot of things. It could be it re-emulsified. It could be something attacked the polymer and clipped it from 50,000 or 100,000 chain monomers into 10 long chain monomers, et cetera, et cetera. There's a lot of possibilities. It's not super obvious which one of them it is. Stones falling off walls. This, by the way, is the topic that made me realize I didn't know anything about adhesion. There's two adhesives in these systems. One is a stiff inorganic polymer, Portland cement. The other is a flexible organic polymer. So we add, we put these rubber additives into cement these days to make thin set adhesives. So in this case, the failure is right at the interface, mostly. So it's most likely that the surface bonds were lost. But it's possible that some intermingling got clipped or et cetera. It's possible that the polymer actually just totally broke down, so it lost its ability to dissipate crack propagation forces. Or it's possible that the polymer actually cross-linked more and became stiffer, and that stiffness became a real problem, or that it somehow created more and stronger surface or a problem. You'd think more would be better. It's not. It's worse.
Could you talk about the role of pressure on like adhesive films or tapes?
So, sure. Let me I got like two more slides, and then I'll talk about pressure-sensitive adhesives, PSAs. I know somebody's going to ask me about that. Skip that one. So this is the Boston Tunnel. The ceiling collapsed in 2006. Unfortunately, somebody was killed in the collapse. But this was an anchor bolt adhesive failure, okay? And these bolts were drilled and set into the concrete ceiling with epoxy adhesive. The total cost of the epoxy in the tunnel was $1,287.60. The repair was $54 million. Oops. So this is just an image. Okay, it's just a bolt into the whatever. And these are images of them after the fact. They just pulled out. This was bad material rheology, mostly, okay? Just very slowly over time, the bolt slowly came creeping out. And they have pictures of this. The short story is there just wasn't enough what I'm going to call rigid entanglement. There was plenty of entanglement, but it was able to very slowly relax over time. And that was enough to allow the load of these concrete ceiling panels to pull the bolts out. So all of these systems were tested while the tunnel was under construction. They all passed their short-term load tests. They didn't give them a long-term load test, but they failed the long-term load test. So,
Was there seawater seepage in there?
no, not as far, no. So this is just a list of books that if anybody really wants to learn about adhesion, I would recommend. That's the end of the presentation. Thanks for your time. So, in case you didn't hear it, this fellow asked me about, hey, can I talk about pressure-sensitive adhesives and the role of pressure, right? That it, more or less? So the first thing to know is that pressure-sensitive adhesives are not pressure-sensitive. If you apply more pressure, they don't get stronger. And I'm going to just assume you really want me to talk about pressure-sensitive adhesives and tapes and that sort of thing, right? That's a very long, complicated topic. It's like deserves its own chapter in the book of adhesion. But the short story is, the rheology of the adhesive that's on the tape has to be just right, like Goldilocks just right, okay? And when it is, that adhesive actually does a nice job of wetting a reasonably smooth surface, okay? And it actually wets itself. The purpose of rolling and pressing and all that is to get out the major imperfections, okay? The bubbles, the whatever, ups and downs. Once those are out, the adhesive does all of its own work because of its own rheology. If it didn't do that, it would be a crappy PSA. Then once it's in position, all of its behavior is all those things I described earlier. It makes weak, crappy surface energy bonds with the surface. And then there's internal entanglement within itself. Sometimes there's 2 or 3 layers of adhesive to get back to the tape. The cover, whatever the hell that's called. That material is actually very important and imparts a lot of mechanical abilities to the whole thing. So I don't know if I answered your question, but I talked for long enough.
Last question.
My experience of adhesives is I can stick something down with tape and I'm like, this is never going anywhere. But then like it cycles through temperature and humidity and it's gone.
Yes.
Can you maybe talk about sort of what's going on there?
Well, it could be a lot of things. So again, the failure, and I'm assuming you mean it's like come undone, or like, let's call it fish, let's say it fish mouth at one end, okay? So fish mouthing is an interesting thing. So some force started to happen within the material for some reason. Maybe it's something volatilized. Maybe the heat caused it to either shrink or expand. I don't know what, but just imagine one of those things. In a lap joint, all of the forces, as it turns out, are at the edges of everything, okay? So as it pulls, that's where it releases, and that's why it creates a fish mouth. Thank you. Mic drop.
All right, we got 2 quick announcements.